As you may remember, at least I hope you do remember, we formulated the weak equivalence principle in terms of something we called test particles. Test particles were defined as bodies satisfying a number of conditions. One of those conditions, and which is the one that concerns us today, was that their gravitational binding energy had to be much smaller than their rest mass energy mc squared. The justification for this was that, we expected gravity to couple to energy instead of mass, as in the Newtonian case, because energy and mass are equivalent, and energy, if you want, is the concept that includes mass. But then we would have to face the question of whether this gravitational binding energy couples to gravity the same way other energies do. And we didn't want to face that question. Then, when we formulated the Einsteinian equivalence principle, we constrained also its applicability to all laws of physics, but except for the gravitational ones. So all laws of physics should take their special relativistic form in any freely falling frame, except for the laws of gravity. So this refers only to non-gravitational laws. And we justify the restriction in terms of the absence of a special relativistic theory of gravity, that in fact there is no such a theory, and we don't expect such a theory to exist. And this is the main reason why we are trying to go beyond special relativity into general relativity, guided by the Einsteinian equivalence principle. If there was a special relativistic theory of gravity, we could just learn from it whether gravitational binding energy behaves as the rest of energies. If gravity couples to gravity the same way that gravity couples to electromagnetism or any other interaction or kind or matter. The strong equivalence principle is meant to go beyond these restrictions. It has the same formulation as the Einsteinian equivalence principle, but there is no restriction to non-gravitational laws. Now, the formulation of this principle cannot be very precise because there is no special relativistic theory of gravity, and then it is not clear what is meant by the statement that gravity should take its special relativistic form in any freely falling frame. However, there is another way of relating gravity to a special relativistic theory, which is the weak field limit that we are going to discuss. There are also other consequences of eliminating the restriction to non-gravitational laws. The most obvious of them is that in the Einsteinian equivalence principle, we consider all laws and all fundamental constants of physics had to be constant in space and time, but the gravitational one. So the gravitational constant Gn now is supposed to be constant in space and time according to the strong equivalence principle. Okay, and this is something that we can try to test experimentally. As for the coupling of gravity to gravity, this is a complicated thing. If we just think of the gravitational energy, we said that there was no standard gravitational energy density, that this could not be defined because in fact the Einsteinian equivalence principle told us that it could be set to zero at any point. However, there is I don't know if to call it a trick or what, if at least in the context of metric theories of gravity, which is we can study the weak field limit. We are going to study this limit in more detail later, but we can advance how it works or what is all about. So, in the if we have metric theories of gravity, so this is only for metric theories of gravity. Gravity is described by this generic metric tensor G mu nu, some gravitational field. When gravity is very weak, well, if there is no gravity, we said that this metric should be the Minkowski metric. If gravity is very weak, it should deviate very little from the Minkowski metric, and we can call this deviation h mu nu. Now you can take the equations of whatever metric theory of gravity and expand them to first order in this h mu nu, which is supposed to be very, very small. What happens, as a matter of fact, is that this h mu nu behaves as a special relativistic field moving in Minkowski spacetime. And approximately this h mu nu describes the gravitational field in Minkowski spacetime, so it gives you a special relativistic theory of gravity. So what's wrong with what we said? Well, what's wrong is that this theory is not really consistent. Okay, it has certain consistency problems that we can discuss later on. However, this theory is a good approximation. In fact, it's a good approximation to the full theory described by h mu nu if you consider higher and higher orders. In principle, if you consider expanding your theory to infinite orders in h mu nu, you may recover the exact theory with full or written in terms of g mu nu, completely consistent. If you truncate to any finite order, in general you find inconsistencies. Okay, so in terms of this field, you can discuss whether gravity couples to itself, so h mu nu couples to h mu nu, as it couples to any other kind of matter. Gravity couples to any other kind of matter as we have advanced through the energy. The energy is part of the energy momentum tensor, and this h mu nu will couple to the energy momentum tensor of all the fields. And then you can look into your theory and see if this h mu nu also couples to the energy momentum tensor of gravity. Well, and then you will ask, is there such an energy momentum tensor? Because you just said a moment ago that there is no energy density that you can define. If you cannot define it, then the corresponding energy momentum tensor should not be well defined. And indeed, it is not. It is only approximately well defined to the same order at which we are working in this h mu nu. But this approximation is really good. It is a very useful tool, and if you understand what are the limitations, you can find many interesting things with it. Okay, so for instance, you will learn that general relativity, okay, in general relativity, which will be a metric theory of gravity, so it is written in terms of g mu nu, the equations expanded in this way tell you that h mu nu couples to the energy momentum tensor of h mu nu itself as it couples to any other energy momentum tensor. This means that gravitational binding energy or any other kind of gravitational energy will behave in a gravitational field just like the rest of energies, and that in the end this means that general relativity satisfies the strong energy principle. The strong equivalence principle. Okay, this is the main lesson. In fact, it is possible to show that if you construct any theory of gravity, any metric theory of gravity, that satisfies the principle of general covariance, then satisfies the strong equivalence principle. Okay, this is good for the theories, but now we have the question of whether this is what happens in nature or not. How can we decide if the strong equivalence principle is satisfied in nature? If it is satisfied in nature, we should discard, we can believe that the metric theories of gravity satisfying the principle of general covariance are good theories of gravity or good candidates. If it is not satisfied in nature, then we can throw all these metric theories of gravity through the window and start searching for something else. So how can we test the strong equivalence principle? The main idea that a guy called Nordtvedt had was that if you consider astronomical bodies with different binding energies, okay, you could say that the part of the total active or passive gravitational mass that corresponds to standard matter and energy here and here fall exactly in the same way because of the standard equivalence principle, but maybe the contribution of their binding energies falls in a completely different way. Then this means that the bodies will behave in different ways in a gravitational field. So the idea is that if there is such an effect, okay, you can parameterize the gravitational mass as the inertial mass plus some parameter, okay, and which reflects the contribution of the gravitational binding energy omega. This gravitational binding energy can be computed approximately. Okay. It is a half of the matter density times the gravitational potential of the own body. Okay, and this is the order of g m squared divided by the radius of the body. Okay, in a certain approximation. Then the question is whether this eta is 0 or not. If it is different from 0, then this will tell us that there is a difference between mg and mi, and that this difference is really due to the gravitational binding energy. Okay. If the motion of when you see that the motion of two astronomical bodies is different because of this reason, this is what could be called the Nordtvedt effect. Okay, and we can advance that nobody has measured a Nordtvedt effect, and there are bounds to its existence, which means that the strong equivalence principle seems to be satisfied, at least this consequence of the strong equivalence principle. The setup that Nordtvedt conceives to study the motion or to study the different motions of two bodies in a gravitational field is the following. So consider the moon, well, consider the Earth first, and consider the moon moving around the Earth, okay, and both of them in the gravitational field of the Sun. Okay, we will represent the moon by this symbol, the Earth as this symbol, and the Sun by this symbol. Okay, so what would be the acceleration of the moon towards the Sun? Okay, this is given by minus the Newton constant, the mass of the Sun that creates this field, divided by r squared. the difference between the distance of the Earth to the Sun and the Moon to the Sun is negligible in this approximation. It's really small with respect to the distance between, the overall distance between the Moon and the Sun, or the Earth and the Sun. They approximately equal. So, and then you multiply the mass of the gravitational mass of the Moon divided by the inertial mass of the Moon times a vector which is directed from the Moon to the Sun. Sorry, from the Sun towards the Moon. Okay, and this would be minus gm divided by r squared, and okay, using basically this definition, we would have 1 plus omega of the Moon, sorry, multiplied by eta, so it's eta omega of the Moon divided by the inertial mass of the Moon and this unit vector. Okay, for the Earth is more or less the same. You get the acceleration as the force divided by the inertial mass. Okay, so we replace everywhere the symbol of the Moon by the symbol of the Earth, and now you can take the approximation that this unit vector is also very close to this unit vector. Okay, so what is the difference between these two accelerations? Okay, this would be the acceleration of the Moon minus the acceleration of the Earth, and there will be a common factor eta, then the gravitational binding energies divided by the inertial masses, and with the common factor of the mass of the Sun divided by the distance to the Sun, and u, which we can take one or the other, the unit vector goes in direction of the Moon or the Sun. Okay, this is now of the order of 2.6, because you can calculate all these things. So this would be of the order of 2.6 10 to minus 12 eta meter second minus 2. How can you measure this, or how would you measure this? Okay, if there is a difference in accelerations towards the Sun, when you see these two bodies, you forget about the Sun. Okay, and when you move in the coordinate system which is co-moving with the Earth, okay, you are in free fall around the Sun, and the only thing that you observe is the Moon moving. The Moon is moving also in free fall around the Earth and around the Sun. And but if there are different accelerations, okay, when you view this from a Newtonian perspective, these two accelerations towards the Sun would be different, and what free fall would mean for the Earth or the Moon in the field of the Sun could be different. This means that you could see something like the Sun here, and okay, the Earth here, and this you could see some polarization of the orbit of the Moon towards the Sun. Okay, it could be like this, or it could be like this. The point is that it could be different than what you see from the Earth. Now, the position of the Moon is known with a huge precision thanks to the lunar laser ranging experiment which they send a laser ray to the moon, and it rebounds, and then you can measure the time it takes for the laser ray to come back, and then the position of the moon with a high precision. And this is thanks to some mirrors that the astronauts left on the moon, which is a proof that somebody was there. Okay, so measuring with very high precision the orbit of the moon around the sun, it has been concluded that eta, okay, is minus 0.001 plus minus 0.0015, which is compatible with eta equals 0. Nobody has, well, you can say that it has been measured, but you cannot distinguish the result from eta equals 0. The reference is given in the lecture notes, so I will not copy it here. Okay, and you could also use this result as a test of the weak equivalence principle if you forget about the origin of this difference between the gravitational mass and the inertial mass. Here we are saying that it is due to the gravitational binding energy, and this allows you to compute these omegas here and these m's and this number here. But suppose that you just ignore what is the reason between this omega, okay, and this, then you can use this as just a test of the equivalence of between gravitational and inertial mass, or the weak equivalence principle, and this tells you that you have a precision. The weak equivalence principle is satisfied with a precision of 10 to the minus 12. And this concludes this video and this lecture on the equivalence principle. Now that we have formulated it and we have found that it tells us that we have to construct theories which are covariant under general coordinate transformations and based on a metric, the next step would be to try to construct a theory of those characteristics. But in order to do that, we need to define several mathematical concepts that we need for technical reasons. Otherwise, we would never be able to construct those theories. Einstein himself had to study a lot of these concepts, okay? So we will have to follow his steps.